The roller coaster Earth. If you'll humor me then, I'll present below a brief summary of all the different motions in play that impact the Earth's orientation to the heavens. The first and easiest to appreciate is the Earth's rotation around its axis, which gives us our cycles of day and night. At the equator, the spinning of the Earth occurs at about 1,038 miles per hour. People standing on the equator have no appreciable sense of that rotational speed unless they're watching how quickly the sun moves relative to the horizon at sunrise or sunset maybe, and it's very much happening all the time nonetheless. The next motion we're taught in grade school is the Earth's annual orbit around the sun. That orbit is elliptical, and the Earth travels faster through space in the winter months when the northern hemisphere is ironically closest to the sun, and a bit slower in the summer months when we're furthest from the sun. But taking an average, we're whizzing that ellipse at a speed of about 64,800 miles per hour, a fair clip by any standards of motion we experience here on Earth. Even though we're closer to the sun in winter, our hemisphere is tipped away from the sun's most direct heat thanks to our 23.44 degree axial tilt, which is why it's colder for us in winter. More about that axial tilt later. A third motion that the whole solar system and the Earth along with it is undertaking is its rotation about the center of the Milky Way galaxy. Since the initial formation of the solar system more than 4 billion years ago, we've made just over 20 trips around that circuit, and will likely make another 22 trips before the sun goes nova and dies. Long as the period of rotation is, the distance covered is huge, which ends up having us travel that orbit at about 828,000 miles per hour. As we loop around the center of the Milky Way, it's also worth noting that we're also bobbing up and down relative to the central plane of the galaxy. We're currently about 68 light years above the galactic plane, but we're moving down towards it and will eventually, over the course of millennia, bob below the galactic plane a ways before bobbing back. That up and down motion adds very trivially to the speed of our galactic orbit. I'm not confident enough in my calculus skills to noodle out the speed particulars though. A fourth motion involves an even grander scale. Our Milky Way galaxy is crashing headlong towards the Andromeda galaxy, our bigger brother in the local group of galaxies to which we belong. The speed with which we're racing toward that calamity, about 312,000 miles per hour. A fifth motion has our local group of galaxies, including both the Milky Way and Andromeda, flying through space towards a mysterious area called the Great Attractor, probably a concentration of dark matter, whatever the heck that is. We're whizzing across that distance fastest of all, traveling something like 1.4 million miles per hour. There's some very recent thinking that the whole universe is rotating somewhat slowly, as a way to explain differences in our measurements of how fast the universe is expanding. That's still very speculative, so I won't even try to include an estimate of what speed our local group might be traveling in that dynamic. Beyond those motions to which one can associate speeds through space, there are a handful of others that are better thought of as wobbles and bobbings. As the Earth spins on its axis, it's tilted askew, and that's responsible, as suggested above, for our experience of seasons. That having been said, the direction of the axial tilt changes very slowly over time in a process called axial precession. The net result? Over the course of generations, the North Star to which the North Pole points, well, it changes. Sure, projecting the North Pole into space currently points toward the star Polaris, but dial back the calendar to 3000 BC, and because of axial precession, the North Star back then was Thuban, a star in the tail of the constellation Draco. Looking ahead, in the year 14,000 AD, our North Star will be Vega, the fifth brightest star in the sky, situated in the constellation Lyra. The whole tilt change sweeps out a circle over a period of about 25,800 years. As that axial precession makes the direction of our North Pole circle over those years, the impact of the moon's tug causes a very minor additional vibration in the circle that axial precision cuts. That vibration is called nutation, and it happens in a cycle of 18.6 years. A further, even more minor wiggle in our axial precession is called the Chandler wobble, and it repeats in a period of about 433 days. Its impact is trivial to night observers, but I suppose it's detectable by powerful telescopes tracking our observation of very distant objects over time. Yet another kind of wobble has to do with Earth's orbit around the Sun. Yes, our planet's orbit is elliptical, but that ellipse doesn't trace the exact same path through space with each passing year. It gets a little bit ahead of itself, and so it traces out a repeated series of slightly offset ellipses. That variation in the motion of the Earth is called the apsidal precession, as contrasted with the axial precession described previously. The time it takes to make one complete flower-shaped spirograph motion and start tracing out another is about 112,000 years. Finally, as it spins and wobbles, the Earth also has a bobbing action called obliquity. The bobbing happens in a 41,000-year cycle and has the impact of tweaking the distance from the Arctic and Antarctic Circle to their respective poles. That's the extent of my knowledge on all these motions, certainly as they apply to the Earth in their current context. It may not be surprising, but many of the obscurer ones toward the middle of the list are also common to our planetary neighbors. Teasing just one example, because each has a different axial tilt, each planet in the solar system has a different effective North Star. A curious thing to consider at first, but not all that surprising when one gives it some thought. The other curiosity is how many of these motions have changed over time. For example, when the Earth was brand new some 4.5 billion years ago, its rotation wasn't over a period of 24 hours. Rather, it completed each spin around its axis once every 10 hours. Yup, 5 hours of daylight followed by 5 hours of nighttime. Interesting forces have caused our rotation to slow over those billions of years. In the end, though, about all I can say is this. Life certainly seems dizzying enough without consideration of this astronomical mega tilt-a-whirl going on around us. Thank goodness we're spared the extra disorientation, cozy in our little, local, day-to-day lives.